My name is Houda Haidar, and tonight we will be asking one simple question. How can something as small as dust build, hide, and even power the universe? And by the end of this talk, I hope that you will all agree that the phrase that you see in your screen isn't just a wordplay, but that dust is really something we can trust. So, the first thing that I would like to introduce is why you should care about dust. Well, it rains down on us. There is estimates that suggest more than 100 tons of cosmic dust fall on Earth every single day. In fact, there is a whole field of science where astronomers go to Antarctica and collect pristine space dust that fell on Earth. You can see an image here of what that dust might look like. And you might think Antarctica, out of all the places. Well, Antarctica is almost like a perfect desert. So when you go there, you can just scrap off dust grains from ice and take it to a laboratory and study it to understand its compositions and maybe even reveal the history of all the things it has gone through. Now, what I find even more interesting, and this has picked up in the past couple of years, is that so many astronomers have found that there is even cosmic dust grains on the rooftop of certain big cities like Paris and Oslo. And you've got some people that are not necessarily astronomers that just go and look for this cosmic dust and they collect it and they sell it to scientists like myself. And scientists then go through that and try to understand how does this dust form and if it could reveal some information about the universe. For example, the dust here that was found on Paris could tell us a bit more about how the solar system was formed at the very beginning. Now, for astronomers, we care about dust because it is simply everywhere. And depending on what kind of astronomer you are, and hopefully by the end of this talk, you will try to gather why sometimes dust is more of a problem and why sometimes dust is more of like a fun thing to study. So if I would look at this, I would say dust is everywhere because I'm someone who really enjoys studying dust. But other astronomers that have dust as a problem, they would look at that and say, oh, it's really everywhere. It's getting annoying because the universe is a very dusty place. In fact, dust is both a subject and an agent of galaxy evolution because dust shapes how we see the universe. It blocks certain objects, so we can't see when you've got dust in certain wavelengths. And in other cases, it reveals them in the mid-infrared. Dust is also the building blocks upon which stars and planets are formed. It also drives the chemistry in galaxies. And it's literally filled in this image that you see, which is Stephan's quintet. You can see it filling the gap between galaxies, glowing in red. You can see it in the spiral arm of galaxies. You can even see tiny speckles of red, which are basically very far away galaxies and are very dusty as well. And because we have dust everywhere, and because dust is a central engine on how chemistry is evolved in galaxies, it really drives the evolution of galaxies. It's also a reservoir of many elements like oxygen, carbon, and iron. They're all kind of locked up in dust grains. And it also regulates the temperature in space. But more importantly for me, because I am a huge fan of supermassive black holes, it is a crucial component in supermassive black holes. And I'll get to later on an introduction on supermassive black holes and how dust is really key to understanding how they evolve. But now let's take a step back and ask the question, what is exactly space dust? Here you've got a real microscopic image of a single interstellar dust grain blown up 100,000 times. I want to stress that cosmic dust is not the normal house dust that we are used to. It's much tinier, and you can think of it more like smoke. You've got solid particles floating in space, filling the gaps between stars and galaxies. And a typical grain is made of three ingredients. You've got silicate, which are tiny bits of rock and glass. You've got carbon grains, which are soot-like specks rich in graphite. And you've got, fancy word, polycyclic aromatic hydrocarbons, or PAH for short, which are these flat rings of carbon and hydrogen. And if you've ever had roasted coffee, if you had a coffee this morning, or if you enjoy a barbecue, you have met PAH, because that's smokiness is basically what PAH is. So these are very small particles, but how small are we talking? Now, down to the left is our cosmic dust. You can see it's under 1 micron in size. And then as you slide up the bar, you've got bacteria, which is about 3 microns. You've got red blood cells, which are about 8 microns. You've got grains of salt, which are 60 microns. And then you've got a human hair, which is a whopping 180 microns. So each grain is smaller than anything that we could ever see with our eyes. But spoiler alert, tiny is not necessarily mean weak, but in the case of dust, tiny is actually mighty. These grains will shape stars, planets, supermassive black holes, and eventually us and life as we know it. So I will not touch on how dust is formed and processed. Now that we know what a dust grain is, where do all those grains actually form? And what happens to them next? Well, dust is born in the outflows of dying stars. You can picture an old giant star, its outer layer, puffing and puffing away. In that cold wind, atoms of oxygen and carbon join up and they condense and form fresh stardust. Now, those newborn grains, they drift in the vast interstellar medium, which I show here in purple, or what we also call for short ISM. And it's a mix of gas and old dust. Out there, dust is leading a very busy life. The dust grains are picking up icy coating, they're getting stripped in radiation, they collide and shatter, and they grow over and over again by coming up together and forming like an even bigger grain. Now, all of these processes are reflected in the different grain sizes that you see. So, for example, you see that the grains are of different sizes, and they're also of different compositions as well, and even different temperatures. So when we study dust grains today, we're not seeing a pristine footprint from a star, but dust that has been reshaped and recycled over and over and over again. We are seeing dust that has been essentially traumatized. But it's bad for the dust, however, it's good for us because it provides us with a record of the chemical chemistry of the universe along the way. It's providing us a record of what happened in the universe. So every time you study your dust grains, you can reveal a little bit more on what occurred to it in the past. Now, of course, space isn't always gentle and dust can get destroyed. This is most likely to happen when shock waves are present. So everything that you see here is gas in violent motion. You've got the bright core in the middle, which is racing upward. And then you've got the darker gas around it, which is almost still, like not moving as fast. So where the fast gas and the slower gas meet, there is a thin boundary layer that is formed, and that boundary is a shock front. which is the exact spot where the fast gas slams into the slower gas. And you can think of shocks also. Sometimes we hear like an airplane, and then we just hear like a boom effect because the speed that it was going through was faster than the speed of the medium, and you just hear that boom effect. Now, those boom effects are very ubiquitous in the universe, and you can find them everywhere, and we refer to them as shocks. Now, what happens to dust when it's facing a shock? When dust grains are caught up under shocks, they can undergo mainly two processes. They can either shatter, you've got like dust grains that are speeding up and they start beating each other and they smash into each other at thousands of kilometers per second, and they start fragmenting and forming smaller and smaller and smaller grains. Or another process is called sputtering, where you've got hot ions that are blasting the grain surface, eroding it. It's like eroding it atom by atom. So we see that grains can die here. But what we have to know is that these fragments, the erosion and the shattering, doesn't completely disappear the dust. In fact, this dust then drifts away in the ISM, or the interstellar medium, ready to be recycled again. So what I would like you to really take from here is that dust is a constant cycle of birth, destruction, and rebirth. Now, those very fragments of dust that are drifting away in space, they eventually settle in a galaxy. They start going down in the galaxy's core, the heart of the galaxy, knitting together into a dense donut shape that plays the ultimate game of hide and seek. And it's concealed in what I would like to call the brightest yet the darkest object in the universe, which are supermassive black holes. And that's my area of expertise, and that's where I study dust. So I really can't help but introduce it. So I would like to take a step back and explain what are supermassive black holes and how dust is playing this hide and seek game with them. So supermassive black holes are these cosmic monsters that are in the center of almost every single galaxy in the universe, including our own, the Milky Way. And they are millions, if not billions of times the mass of the sun. And we've got a couple of theories on how they would have formed, but it's not, we still can't tie that properly. However, we know that it all boils down to the collapse of a massive star that left behind a black hole seed, and that seed eventually grows by accreting gas and dust around it, or by merging with another supermassive black hole and creating an even bigger supermassive black hole. Now, at some point, these black holes can no longer accrete material. So they start burping that energy back. And that's when we refer to them as active galactic nuclei, or AGN. Galactic nuclei because it's in the nucleus, i.e. the heart of the galaxy, and active because it's actively feeding energy into the system by launching jets and winds out. And this process is called feedback. And I'll just take a second here to explain what feedback is. Now, imagine you've got fast winds that are blowing anything, any gas or dust that is around the supermassive black hole, is blowing it away. And it's heating it because the temperature that it comes at is really, really hot. And this means that the black hole, which relied on the dust and gas around it to feed on, has no longer any food. Therefore, the supermassive black hole stops growing, and star formation also stops. At some point later on, after hundreds of millions of light years, the gas cools down, And then the black hole has this ability to feed on more gas and dust because it's now more settled. And then at some point, again, if it's so full that it can't consume any more material and it starts ejecting energy back. So you can see that this AGN feedback can happen at many different cycles in the lifetime of a supermassive black hole. And now I want to show you a real image of an active galactic nuclei in action. Everything glowing in orange and blue is powered by a single point that you cannot even see at this scale. And just take a moment and think about it. One object is shining brighter than all stars combined in the galaxy. That, for me, is the most mind-blowing thing that happens in the universe. I might be biased because I'm very keen and I really passionate about supermassive black holes, but it's absolutely outstanding to see this in action, capture like this. So how do you hide a supermassive black hole that is brighter than the entire galaxy? The answer is, of course, with dust, because all of this is all about dust. So how does dust play this game of hide and seek? We have here an artist's impression of what an active galactic nucleus shrouded and surrounded by dust looks like. It's basically forming a donut, a thick layer of dust. This dust eventually goes inside the supermassive black hole for it to be to feed on. But the most important thing is that what's really a big question for scientists is that depending on your viewing angle, so if we're lucky to look straight down the hole in the donut, like this direction, we can see the central engine, and therefore we refer to this AGN as type 1 AGN. But tilt the galaxy a little, and our view cuts through the donut, and all the visible and the ultraviolet light is absolutely blocked, and the core disappears. And that's when we're talking about type 2 AGN. So you've got the same beast, just hidden behind a dusty donut. And this is an active area of research because scientists are trying to understand if the difference between type 1 AGN, which is this case, and type 2 AGN, which is this case, is it purely based on this dust that is blocking our view, or is there another element, like an evolutionary element, where the black hole potentially has evolved, and that's why we see the difference? So this is a big question that scientists are actively trying to answer, including myself. However, to really catch the monster in its favorite hiding place, we need a different kind of light. One that dust can't keep to itself. And that light is called infrared light. That's basically heat. So if you get a temperature, if like you get heated up, then you are basically emitting infrared emission. We are currently emitting infrared emission because as humans, we always have a temperature, but you can't see it with your eyes. And the infrared light is really special because all of the dust is emitted in that specific wavelength range. And that's exactly why telescopes like the James Webb Space Telescope are extremely, extremely powerful. One example of how dust hides in the visible light and is released in infrared is the Barnard 68 example. So to the left, you've got an ordinary starlight, and you've got just like a black blob, and dust has swallowed every single photon behind it. To the right, we switch to the infrared, and there you have it. Thousands of hidden stars are popping out, even stars inside this cloud that we would have never guessed that anything is there. But with infrared light, you're able to see it. So the infrared light is quite literally turning the lights back in the universe. And even though it looks like magic, it really isn't. This is because dust is simply glowing in the infrared. And what I would like to stress here is that not all light is created equal. And light comes in many forms and many wavelengths. You've got lights from gamma rays all the way to radio waves. And our vision, us as humans, is very limited to a very small range. So I pointed here to where exactly the visible light is. But currently, in your room right now, or wherever you are, if you look around you, you're only looking at that small visible wavelength range, and you're missing so much light that is coming from different wavelengths. In fact, if you're watching this on your laptop has a temperature, and if you put a infrared camera on it, it will glow because the temperature is glowing in the infrared. So now, by switching to infrared, we just don't see through the dust. We actually see the dust itself light up and glow. And that's exactly why NASA poured 30 years on a mission and $10 billion to build the most powerful telescope on the planet, which is the James Webb Space Telescope. And I am very lucky that I got this year time to study supermassive black holes with the James Webb Space Telescope. Acceptance rate on this is really, really low. Like it's less than 10%. And everyone wants a piece of JWST. Everyone wants to be able to tell the telescope, go and point this way. However, the telescope has only limited time. So that's why the competition is really fierce. So I'd like to spend a couple of minutes introducing the James Webb, which is currently parked 1.5 million kilometers from Earth in a quiet spot called L2. It was launched on Christmas Day in 2021. I was so excited. Me and my friends, we did like a whole JWST launch party. And it essentially, when it was launched, it was unfolded as a butterfly in space, thanks to its hexagonal shapes. If you were ever wondering why JWST has these hexagonal shapes, so that you can actually fold it, put it in a rocket, and when you send it up, it can open up because the mirror was so big that you can't just fit the mirror open as it is. And what's really interesting is that it had 344 single point failures. That's more single point failures than the Apollo mission, meaning it was completely mission impossible. And most single point failures were linked to the sun shield, which is in pink here, because it's made of thin, almost like aluminum foil. So scientists were really worried that when it's going to go to space and open up, it's going to start ripping. And that would have been a problem because the sun shield is the hot phase of the telescope, and it basically faces the sun and it takes up all the heat so that the cold place is protected from any hot temperature that would eventually come from the sun. And the cold phase is where you have your obviously your mirror, but also behind the mirror you've got all your instruments. Now you might be thinking, why do the instruments and the mirror needs to be in a very cold temperature? Well, knowing that you are trying to pick up infrared emission, i.e. you are trying to pick up temperature, that's thermal emission, you don't want to be picking up your own temperature or temperature that is coming from things, from the instruments heating up. So you want to make sure that your instrument is in complete cold, icy temperature. Is actually minus 230 degrees Celsius. So that if you're picking up any temperature, you know it's temperature coming from dust from like a very distant galaxy or a supermassive black hole shrouded and covered by dust. The James Webb Space Telescope is made of four instruments, like I said. The mirror is 6.5 meters in size. That's massive. And that's why exactly they needed hexagonal shapes so that it closes. And the sun shield was also folded, and then we went to space. We just opened it up. So there is so much engineering that went into making something so intricate and so beautiful, and at the same time so functional, that we are truly lucky to be living in this era, that we're able to create instruments like this and also get useful science out of it. So what kind of science is JWST really pushing for? Webb was built to tackle two time zones of the universe. On the left, our cosmic neighborhood. It studies things that are hidden by dust, so like newborn stars, planets, active supermassive black holes. And on the right, very, very close to the Big Bang, its aim is to hunt down for the very first galaxies that were ever formed. And I would like to show one of my favorite Webb images, which is for the fiery hourglass. This is stunning. It basically looks like a cosmic butterfly, but in reality, it's a baby star in the making. It's a stellar nursery, and it's only about 100,000 years old, still hidden inside a very dusty cocoon. And you can see in the center is the accretion disk. But what you're seeing with Webb is not only infrared lights that is showing different colors, but it's actually showing action. It's capturing action. Those pink filaments in the lobes are molecular hydrogen that has been shocked, literally slammed and heated by material that the baby star keeps firing into. And all that turbulence stirs the cloud so violently that it stops any new stars from forming nearby. And this proto star will end up claiming most of the raw material to itself. Now, the thin dark line in the center is the star's accretion disk, and it's basically a swirling plate of gas and dust that will end up one day forming a couple of planets, or a bunch of planets, or thousands of planets that will be orbiting this star at some point. And if you were not impressed enough, I would just like to throw in what you would see if you did not have infrared, and if you were just looking in visible light, i.e. with our eyes, you completely see pitch black, nothing. And then you put in infrared and you have this magical image of a protostar in the making. So Webb has done so many discoveries. I would like to touch on some of the pretty images that it has released. But I'm sure some of you have seen many of these already. We've got from nearby planets to colliding galaxies, the infrared images that we've been capturing from JWST just keep finding dust everywhere it's looking. So let's do a quick tour. So let's look at the Phantom Galaxy. This is a face-on spiral, which is tracing dust lanes. You've got these dark swirls right into the blue hot core, and they outline where future stars will potentially form. So that's really cool. We've got the Cartwheel Galaxy. This is basically a head-on collision that turned this galaxy into a giant dusty ring. You can see like the dusty ring around it. And Webb's mid-infrared view shows us these shock waves where dust is heating up, breaking, and starting a new burst of star formation. And then we've got Jupiter, which is a bit closer to home, and you have this hazy glow on the Jupiter's poles, which is basically tiny dust and ice grains that are high in the atmosphere and that are made visible with JWST. So wherever JWST points, it's picking up dust. And on at least one small rocky planet, ours, dust helped kick-start life. And I want to wrap up the talk on what I've promised, which is how dust shapes our life. So let's bring the story home and see how dust has made us and life as we know it. Now, as cliche as it may sound, and maybe some people are tired of hearing this, but we are made of stardust. You are made of stardust. Every carbon atom in your DNA, every ion that is running through your blood was made in a star. When those stars exploded, they wrapped the elements inside dust grains and they blew them into space. And eventually it fell on Earth, and that's how we got here. But most importantly, and I think what a lot of, scientists, if I can be honest, are not really appreciative of, is that dust is actually also working as a tiny laboratory. So imagine inside cold, dense parts of a cloud, you've got atoms that are basically looking for somewhere to mingle, to form chemical reactions. And dust grains are the perfect spot for that. A dust grain surface basically works as a laboratory, allows atoms to meet, to react, and to stick together. Let's take water as an example. You've got an oxygen atom, which attaches first, then you've got two hydrogen atoms, which follow. And on the grain surface, they link up and they make H2O, which is basically water. And because the grain sits in only a few tens of degrees above absolute zero, that fresh water molecule freezes up instantly, which is adding this icy coating that you see here. So every dust grain is a tiny chemical laboratory, which is manufacturing water and other simple molecules in the darkest places of the universe. And they end up finding its way to our planet and form life as we know it. And you've got comets, asteroids, and micrometeorites, which are sprinkling dust chemistry on planets, including our own. So all of this happened billions of years ago, which led to, a dusty rain that helped stock the Earth's ocean and eventually life, because everything starts and finishes with water. So I want to finish off by saying, and we'll have plenty of time for questions, which would be very great. We've seen that from newborn stars to dusty supermassive black holes, you've got from tiny water clouds to the iron that is running in your veins. Dust is literally the thread that stitches the universe together. So I hope that we know that in dust, we don't just trust, but we come from it, and we will eventually be returned to it. So I end my talk here. I'd be more than happy to take any dusty questions. I hope you prepared some, and I'll thank you for listening.